Hello, thank you for coming during the summer. We will have our first summer talk by Ilkyoo Choi from Korea, who is now postdoc there doing his military service. He's finishing his second year out of 3 years. So, Ilkyoo, go ahead.
Thank you. Good to be back. I was here last year as well, giving a talk in a different room. So today I'll talk about improper coloring sparse graphs on surfaces. So I'll explain what improper coloring is, and I'll also explain what a surface is. And there are a lot of faces on this slide, but this is not a talk about one paper, it's about like one project or one field. So these are all my co-authors of my 3 papers in this field, and there may be more coming depending on what happens. So this is André Brasfo and some other French people, and some students at KITES who I work with. And this is actually a picture of the ICM held in 2014. We were working on it, and the photographer thought we were interesting, so he took a picture of us, and we were on national news. And we were actually working on this problem, so I felt it was worth putting it up here.
With the same laptop, I recognize the Rubik's Cube.
So it's proof that it's not fake. Okay, so first I'll talk about what a surface is. So a surface is a non-null, compact, connected 2-manifold without boundaries. And I don't like this definition because I do discrete mathematics, and I want to explain everything in terms of discrete stuff, right? Not like this continuous manifold going on. So in order to explain what a surface is, I'll introduce 2 operations. I'll introduce this operation called adding a handle. Right? You have some surface and you add something that looks like this. So this is a handle. It's your coffee cup, right? the handle on your coffee mug. And this thing is called a crosscap. So this is, you just have something flat and you punch a hole and you identify opposite points or antipodal points. So this is called a crosscap. So I'll say an orientable surface is you start with a sphere and you start adding some non-negative number of handles to this sphere. And then I'll say a non-orientable surface is you start with a sphere, but then you have to add at least one crosscap, or you add some number of crosscaps to the sphere, and this will be a non-orientable surface. So I told you I will explain what a surface is, but now I'm explaining what an orientable surface and a non-orientable surface is. So maybe I was lying. But this is not the case, because what I actually told you is all the surfaces, right? There's this theorem that's called the classification of surfaces that says a surface, a general surface, is either orientable or non-orientable, right? It's either here, it falls under this category, or it falls under this other category, that's non-orientable. So you might be thinking, what happens if you start with a sphere and you add 3 crosscaps and 10 million handles, right? Is that orientable or non-orientable, right? Because I've only given you 2 definitions. But what's actually happening here is that 1 handle and 1 crosscap is equivalent to 3 crosscaps. And this is from George Francis's picture book, where he actually explains topology through pictures. He says if you start with a handle and a crosscap, then you can deform these figures and actually end up with 3 crosscaps. So what does this theorem or lemma by von Dijk saying? He's saying if you have 1 handle and 1 crosscap, then you have 3 crosscaps. Right? So if you start with a surface, or if you start with a sphere, and if you add some number of handles and some number of crosscaps, if there exists 1 crosscap, then you can use this crosscap to transform all of these spheres into 2 crosscaps. And now you have demolished all the handles and you're only left with crosscaps. So you fall under the realm of non-orientable surfaces. And if you didn't have any crosscaps at all from the very beginning, then you are, in this case, the orientable case, where you just start with a sphere and you're adding some handles to the sphere. Right? So what I proposed, well, actually did what I proposed, right? I proposed what a surface is. And I explained what a surface is in terms of these 2 discrete operations. Right? So if somebody tells you a surface is some continuous object, you can tell them, no, a surface is actually something discrete, right? You can start with a sphere and you can do something discrete and you can obtain all the surfaces in the entire world. So one more thing to note is that if you start with this lemma, you look at this lemma and you say 3 crosscaps is equivalent or somehow equal to a crosscap and a handle. So this means maybe you want to, as mathematicians, right, you want to simplify everything. So you want to cancel out this 1 crosscap and change this 3 into a 2. So maybe you want to say 1 handle is equal to 2 crosscaps, but this is not true. Right? Because 1, the handle, right, if you start with a sphere and if you add 1 handle, that will be an orientable surface. And if you start with a sphere and add 2 crosscaps, that would be a non-orientable surface. Okay? So even though this statement looks bizarre, you can't simplify this anymore. Right? You can't cancel out the 1 crosscaps on each side. But there's a notion. Yes?
You're implicitly assuming that their surface can't be both orientable and non-orientable. You haven't quite said that yet.
Well, I said something about the boundary. But there's this notion that captures this. Right? This is somehow saying 1 handle is maybe somehow equal to 2 crosscaps, and now you will assign this number that's called a Euler genus. Right? So an Euler genus of some surface is the number of crosscaps and twice the number of handles you've added to the sphere to obtain this surface you have. Right? So from now on, when I say a surface, I actually don't care if it's orientable or non-orientable. I will just think about it as a surface with some Euler genus. So, and I'll denote that as S sub gamma. So the sphere is S sub 0 because you haven't added anything to the sphere. And S sub 1 is just a projective plane because you've added 1 crosscap to the sphere. And now there are 2 types of surfaces if I say S sub 2. Right? This is either the torus, which is the sphere, and you add 1 handle, and each handle is 2, and counts as 2 as the Euler genus. Or you start with a sphere and you add 2 crosscaps, and this is known as the Klein-Bach. So when I say S sub gamma, in general, there are many, many surfaces that will correspond to this S sub gamma, but I don't care which one is which. I just care about which gamma it is, what the Euler genus is. So this is what a surface is. And now I'll talk about improper coloring. So this is what coloring is. Right? We say a graph is k-colorable if you can do 2 things, or if you can do 1 thing that satisfies 2 properties. 1 is that you'll assign a color from 1 to k to each vertex, and 2, you want to say every vertex, every edge is non-monochromatic. The colors of the 2 endpoints of every edge is different. So another way to interpret this is saying you can partition the vertex set of your graph into k parts, and you can also, and the second condition transforms into saying each part induces a graph with maximum degree 0, or at most 0. Because you want each part to be, you want each color class to be edgeless, so the maximum degree would be 0. So for example, you have this 5 cycle, and this 5 cycle is 3 colorable, because I can assign colors from 1, 2, 3 to each vertex, and make sure each edge is non-monochromatic. The colors of the 2 endpoints are different. But this is somehow very close to being 2 colorable, right? Because there's only 1 vertex that requires the 3rd color, and I've only drawn a 5 cycle here. But maybe if I draw a cycle of length 1001, right? Any arbitrary long odd cycle, I can color all the vertices with 2 colors except 1, where this last one needs a 3rd color. So this is very, very close to being 2 colorable, but it's not quite 2 colorable. So this is where improper coloring comes in. Right? So improper coloring, what you're doing is in each color class you're going to allow some defects to happen. You're going to allow some edges to be monochromatic, and we will do it in this way. We'll say a graph is D1 all the way up to dk colorable. If the first condition is the same, you have k entries in this tuple, this is a k tuple, so you want to partition the vertex into k parts, and for the ith part, you want the maximum degree to be at most d sub I. So you're partitioning your vertex set into, so you're assigning k colors, and you want the kth color or the ith color to have maximum degree d sub I. So now this 5 cycle, you see you can partition into 2 parts, where the first color 1, is an independent set. It has maximum degree 0, but the second part has maximum degree at most 1. So now this somehow captures the notion that it's very close to being 2 colorable. So this is what improper coloring is. So now combine the two of the surfaces and improper coloring. So there's this famous theorem by Apple and Hatkin that says planar graphs are 4 colorable. And what this actually means is, it means it's 0, 0, 0, 0 colorable. Okay? So if it's 4 colorable, you're partitioning it into 4 parts, such that each part has maximum degree 0. And to denote that, you just have 4 zeros in this tuple. So maybe planar graphs are somehow 3 colorable. Maybe they're sparse graphs, so maybe you should be able to partition it into 3 parts and have bounded maximum degree on each part. Maybe not 0, but maybe some small number. And this was proven 10 years after by Cohen, and Wodo. They proved that every planar graph is 2, 2, 2 colorable. So if you're not so strict about your maximum degree on each color class, you can partition your planar graph into 3 parts instead of 4, and allow this defect of maximum degree 2 instead of being very strict and enforcing this theorem. And then 10 years after this, or this was the earliest reference I could find, is that these group of people proved that you can't decrease any of these 2's to 1. So they proved that if you give me some k and l, there exists a planar graph that's not 1kl colorable. So you cannot partition an arbitrary planar graph into 3 parts, such that at least 1 part has maximum degree at most 1. So this result by Cohen, and Wodo is very sharp. It's sharp in the sense that you can't decrease this 2 to 1. So this is best possible. And this is actually a construction of this planar graph. And I'll briefly explain what's happening. So here, I claim that x and y in this graph. What's this graph? This graph is you have a bunch of p3s in the middle. You have a bunch of paths of length 2 in the middle. And you just join those paths to these 2 vertices. So everything is adjacent to x and y, and including x and y. X and y itself is an edge. So I claim x and y cannot be colored k and l. Why? Because if x is colored k, and if y is colored l, then if you have many, many of these paths of length 2 in the middle, then there's going to exist some path where you have to use the color 1 on all 3 vertices. Right? Because this x, if it's colored l, it's going to allow maximum degree at most k. I mean, if it's colored k, it's going to allow maximum degree at most k. So this x will destroy the p3, only k of these p3s. But now on this side, since y is l, y is colored with l, it's going to only destroy l of these p3s. So if you have k plus l plus 1 of these p3s in the middle, there's going to exist some path on 3 vertices where you cannot use the color k nor l. So you will have to use the color 1 on all 3 vertices. And that itself is a contradiction. So this was some small claim that you cannot color x with k and y with l. So let me denote this graph with this dotted line. So what's denoted here is that I have this very, very long cycle, and I have a vertex in the middle. And with this dotted line just actually means this construction over here. So what I'm going to do is, so I have another claim. I claim z cannot be colored k nor l. So if z can be colored with l, then by this flip, so this dotted line means if one is k, the other one cannot be l. So if z is colored with k, then all of these vertices on the boundary cannot be colored with l because of this previous claim. And if this path or this cycle is sufficiently long, then there must exist some sequence of 1s on this path. So that will be a contradiction if this cycle is sufficiently large. So now I'll take this vertex z out of this cycle and I'll denote it like this. And now I just combine the 3 of them like this. Because what's going to happen here is not all 3 vertices can be colored with 1. So at least one of the 3 vertices has to be colored with either k or l. And this percolates down, and somewhere you get a contradiction. So this is how most of these constructions are made, or this is one way of making these constructions. So what this actually shows is that improper coloring planar graphs with 3 parts, the question is completely solved. Because if you want to partition your planar graph into 4 parts, then you know we can force them to be all zeros. But if you want to do it 3 parts, you can do 2, 2, 2, but you cannot decrease any of these 2's into 1. So we know everything, and we know it's sharp. So the next question is what you want to do when you partition into 2 parts. Right? And here there's very bad news because everything breaks down. Because if you give me any 2 numbers, I can give you a planar graph where it's not that colorable. If you give me d1, d2, I can construct a planar graph that's not d1, d2 colorable. And this is the construction, but I won't go over the construction. It's somehow similar in the sense that you have this dotted line and this something that's adjacent to all of x and all of y, and you repeat that construction here, and you add all these edges. So this is an easy exercise. So in some sense, improper coloring planar graphs is completely solved. If you partition it into 3 parts, there's some positive answer, and if you partition it into 2 parts, everything breaks. But maybe you want some positive results when you partition it into 2 parts. So what you do is you consider sparser graphs, right? Because planar graphs are somehow sparse, and you want, maybe enforcing this sparseness will give you some positive results. And one of the popular ways of enforcing a graph to be sparse is to enforce this girth condition. You want to make sure there are no short cycles. So you want to say every cycle in this graph is somehow large. Because if this happens, because you're planar, it has to be somehow, even if it's not planar, it has to be somehow sparse. Right? So you can consider these 2 questions. So the first question will be, if I give you 2 numbers d1 and 2, d1, d2, can you find the minimum girth such that this statement is true? Right? You want to find the girth condition that guarantees that every planar graph is d1, d2 colorable. And the second question is you just flip what I just said. Right? Second condition is if you give me 2 numbers where one of them is girth and the second one is just some arbitrary number, can you find d1? So if you give me g and d1, can you find this d2 such that this statement is always true? So you're playing around with these maximum degrees of 2 parts and your girth condition. But now, if you think about this, we haven't used anything of the fact that it's planar. So maybe we can just consider sparse graphs. And one way of measuring this sparseness is this parameter called the maximum average degree. So drop the planarity, forget that your graph is planar, and just say, can you determine the supremum of this maximum average degree that guarantees that your graph is d1, d2 colorable? So there are a lot of questions or 3 different directions where you can investigate this topic. And I'll only talk about the first one, because I like the first one the most. So I'll talk about the first one. So you've seen this graph, the top graph. This is the graph that shows that there's no d1, d2 colorable planar graph. But if you look at this construction that I've shown you, this graph actually has girth 4. So it's triangle free. So it's already a little bit sparse. And even more, if you want to construct a graph that's 0 something colorable, so if you want one of these 2 numbers to be 0, I can give you some construction where it doesn't work when girth is even 6. So if you want one of these 2 numbers to be 0, your girth better be at least 7. So what am I going to do with these constructions is I'm going to have this giant tape. Yes?
Is it obvious that this minimum exists?
No. So, like this. 0, 0, this doesn't exist. So, if you give me this table, I can now construct this table. And I can say, each entry will be the girth. I want to say, well, this entry would be the minimum girth that guarantees every planar graph is 2, 4 colorable. Or this entry would be the minimum girth that guarantees every planar graph is 0, 6 colorable. So now I can start filling in these gaps. So of course there are some results known, actually a lot of results known. So in 2000, Shirkovsky proved that if you let the two numbers be the same, then the minimum girth condition that guarantees your planar graph is this DD colorable is 5. And this is tight because this example was girth 4. So you know there's a graph that doesn't work when it's girth 4. So basically Shirkovsky proved for girth 5 it works. Therefore this threshold is tight. So, but what he actually proved is not only 2 entries, he proved all the entries below. Right? Because there's this monotonicity thing going on. Right? Because if girth 5 guarantees that your planar graph is 4-4 colorable, then girth 5 will also guarantee that your planar graph is 4-5 colorable and 4-6 colorable. Right? If you allow more and more maximum degree, it's just easier to color. So the threshold should not increase. So once you have something blue here, blue means tight. If you have some blue entry here, then everything to the right and everything below will also be blue and determined. So in 2000, Shirkovsky proved these values are 5, so he proved this and this, which means these two columns, everything is 5. And then in 2011, 10 years after, Borodin and Kostochka proved the girth threshold for 2-6 colorability is also 5. So they also proved these two entries, but they actually proved infinitely many values down here, because everything down will also be 5. And then there was a lot of effort trying to figure out what happens in the first column. Because when your maximum degree is 0, that means you're an independent set. So this is somehow like your proper coloring, the classical coloring. So you want to figure out what happens here. And Montassier, Oshem, and Borodin-Kostochka, they proved these values. So they proved every value in this column except for these two. And there was a lot of effort in trying to figure out what the first entry is. Trying to figure out what the girth condition that guarantees that every planar graph is 0-1 colorable is. And it seems like every 1 or 2 years they're slowly improving down. And now we know this is either 10 or 11. So it's one of the two values. And this is everything else. Right? So there are these partial results that figure out that these are blue, and this value, this isolated 8, and everything down here is tight and 7, and everything else is either 1 or 2 values. Most of them are either 5 or 6. These 3 are 6 or 7. This is 7 or 8 or 10 or 11. So this was the state of the art of the problem when I first saw this problem in 2013, like 3 years ago when I was a student. So what happened? What happened was Andrea Raspo was visiting my advisor at Illinois, and he gave this talk, and he saw this question, and he said, well, here this is 5, and this is 4 and 4, so that's 8. And here he said this is 5, and this is 2 and 6, so this is 8. So maybe this value here, right? This value is 3 and 5, so the sum is 8. So maybe every diagonal here, right? Every entry on this diagonal should be 5. So he asked this question that if you're a planar graph and if you're sparse, like girth 5, girth at least 5, then are you D1, D2 colorable when the sum is at least 8? And then, so Montassier is Andre's student, and Oshem is close with Montassier. So they were also looking at this question, and they said, well, it's interesting to see that every column has finitely many values left, except for this first column, or the second column. Right? The second column, nobody knew anything, nobody knew any type values. Right? So maybe they were asking, does there exist some finite D2 such that this is 5? They knew it was 5 or 6, but is there some threshold where we know that's exactly 5? So what happened is Andre, he was in Illinois, and I was working on this problem, and then he left. And the day he left, I solved the problem. Mm-hmm. So this one I solved, right? So this entry, this one looks like the easiest to attack. Right? So I solved this. I said, okay, now this is 5. So I solved this, we typed it up, we submitted it, and then I graduated. And then I went to Korea, and then I met these students at this new place. And then I showed them this table. And then they were asking, okay, which one's the hardest one? And I said, this one. And they said, okay, that's too hard. So they were asking which one's the next hardest one. And then I said, okay, maybe this column, right? Because nothing is known here. Maybe something positive here can be done. And this is what we actually did. We proved that there exists some D2, where G of 1 of D2 is 5. So what we actually proved is if you extend this table a little bit, we actually proved that from 6, if you go down all the way to 10, then this entry is a blue 5, and everything down is 5. So we actually proved every planar graph with girth 5 is 110 colorable. So what does this mean? This means that there's only finitely many values of this table left. So now there's like 15-ish values left. And we were actually looking at this proof, and we realized that we can generalize it to all graphs on surfaces, or to graphs on all surfaces. Well, but you have to maintain this condition that your girth is at least 5. So here we proved if you're planar and girth 5, then you're 110. And here we proved if you're on some surface with Euler genus gamma, remember gamma I explained like 30 minutes ago. If it's girth at least 5, then you're 1 comma the maximum of 10 or something that's linear in gamma. And then we were trying to see if this was tight, and then we found some example where this is indeed tight. So how do you prove that this is tight? So this is just some construction, which maybe I have time for. So this is what we want to do. We want to construct a non-1K colorable graph that's embeddable on some surface of Euler genus K, but linear in K, right? Because we just care that this is linear. So what we do is we start with C7. We start with the cycle on 7 vertices. And this doesn't work. And because this is an odd cycle, when you color it with 2 colors, if I say the colors are 0, 1 or 0K, there has to be some edge that's both colored with K, because you cannot 2-color an odd cycle. AK. And I claim that one of these 3 is 0. Or maybe I should say 1 because we're doing 1K color. One of these 3 is 1 because, one of these 3 is K because they can't all be 1. If it's 1, 1, 1, then this vertex would have 2 neighbors of degree 1. So one of them is K. And I say this is the triple that we're looking for. This is like the good triple. So here it says, given a triple, adding a P3 means you fix 3 vertices, where between x and z there may be an edge. So this is x, z, and y. And you know these 2 edges don't exist, right? These dotted lines mean these edges don't exist. And here I will add this P3. And I will add a matching between this P3 and these 3 vertices. So the idea is, if x, z, and y are colored with K, and if I add sufficiently many P3s, then at least one copy of this P3, you cannot use the color K. So all 3 of them, you must use the color 1, and at that point you have some contradiction. And this is what I proved over here. I proved that there exists some good triple where all 3 of them are colored with K. So this, so I guess I didn't explain how to construct it, right? So you start with a C7, and for every 3 vertices, I just do this operation of adding a P3 many, many times. So once you do this operation, I know there exists 3 vertices that are good for our purpose, and we obtain some contradiction. And if you count the number of edges, you have this many edges, and this is only linear in K, and we know that if your graph with so many edges, if you just add 2 to the number of edges, that's the Euler genus of that graph, or at most the Euler genus of that graph. So we know this graph has Euler genus linear in K. So this is how we construct it. So this is what happened at Keist, and then we went on to graphs and surfaces. So Montassier, we met at some conference. I told him I solved your problem, and then he invited me. So I went to Montassier, and I went to Montpellier, and we were working. And then I told him I was going to visit Grenoble to visit a friend, And he told me you should go work with Espere on this problem. So I went to Espere and we worked on this problem. So what this problem is that, well, you can think of these two results that I introduced in the beginning of the talk as graphs.s0. But if you actually look at their paper, they prove this result. They prove something more than just planar graphs. They said if you give me a graph on some general surface, you can partition it into 4 parts, where each part has maximum degree something linear in gamma. And they were asking, can you do it in 3 parts? So we looked at this question, and unfortunately this was already solved by this sequence of papers. So the first one, they proved it with something linear in 87. 10 years later, Cohen and Jerusalem improved it from linear to something in square root. And then recently, Woodall improved the constants here. So now they know this question is true. Well, they know instead of 4 parts, you can do it 3 parts. So we looked at this, and then we looked at this, and we said, well, maybe we want to generalize these results to something like this. But instead of saying each part is balanced, instead of saying each part has the same maximum degree, maybe we want to put in as many zeros as possible. We want to say many color classes are independent sets, and maybe 1 or 2 you can allow them to have some defects. So this is what we did with Espere. We proved that so every planar graph is 4 colorable, but if you go to a graph on some general surface, you can still partition it into 4 parts, and you can even guarantee that 3 of them are independent sets. But the last one, it's linear. And this is somehow expected, right? Because the maximum chromatic number of a graph on the surface S sub gamma depends on the gamma. Well, not linearly, but it still depends on. So we were expecting some dependency on gamma here. And then we also improved, well, not improved, generalized this, right? They said a graph on a sphere or a planar graph is 2 colorable. And we do the same thing. We say if you give me a graph on some surface, I can partition it into 3 parts, such that the first 2 is the same 2, right? 2. But the last one, we will allow it to have some bounded maximum degree. And the dependency on the Euler genus is linear. And then we were also come up with constructions that these are tight. Well, tight in terms of the growth rate, right? This 9 gamma minus 4 is not tight in the sense that the 9 and the 4 may be improved, but we didn't really care because we just cared about the growth rate. So once we had this result,
So that means linear growth.
linear growth. Yes.
Could you, you mentioned a similar result, that Cohen and Woodall couldn't be improved to 1,
Yes.
D2, D3. Do you have something similar for your second result there?
We used the exact same thing,
Okay.
right? Because if you're planar, you are embeddable on any surface you want. So that means any of these 2's cannot be improved to 1. So we have this, right? So, but the same idea, right? This completely solves the question for improper coloring graphs on surfaces for 3 parts. But now we want to do the same thing for 2 parts. Right? And what do you do when you want to do it for 2 parts? You add these girth conditions. Right? So what do? We say, okay, look at girth 4. What do we know about planar graphs that are triangle free? So girth 4. We know that they're 3 colorable. So they're 0, 0, 0 colorable, and we generalize this. How do we generalize it? We say, if you're a triangle-free graph on some surface with Euler genus gamma, we do the same thing. We can partition into 3 parts. First 2 are 0, 0, and the last part, this dependency of gamma is linear. So what do we do next? We do girth 5, and we show this is tight. So we do girth 5. So for girth 5, remember this result I had with the students at KAIST. We proved that you could do 1 comma something, and we know that this is tight. So you can't do any better. You can't decrease this 1 to 0, and you can't decrease this dependency on gamma to sublinear. Okay. So what do? We go to girth 6. But when you go to girth 6, we can't decrease. Yeah, we can't decrease this 1 to 0 anyway, because this example I showed in the earlier talk, or the earlier section of the talk, So there's nothing, no change happens between girth 5 and girth 6. So now we go to girth 7, and we were finally able to prove that if you're a graph on some surface, and if you're girth at least 7, then we can decrease this 1 to 0. And of course we have this linear term here. Right? And we were trying to look for tightness examples for this, and we failed, and we couldn't find any tightness examples, because this theorem is not tight. So something happens here. Right? From girth 6 to 7, this dependency on gamma changes from linear to the square root. And then we could find an example that it was actually tight. So this actually solves the entire question of improper coloring graphs on surfaces with the girth conditions, right? Because if you go 0, comma, square root of gamma, there's nothing more you can do. So this is a recap, right? This is what we did. So what's happening here is if you have a graph on some surface, then you can do 0, 0, 0 linear and gamma. You can do 2, 2 linear and gamma. And if you start forbidding triangles, you can decrease these 2's into 0. So you can do now 0, 0 something linear and gamma. And now if you forbid 4 cycles as well, I can shrink the length of the tuple from 3 to 4, 3 to 2, but now I can do 1 comma something linear and gamma. And nothing happens between girth 5 and girth 6. And once you hit 7, you can have 2 improvements. One improvement is you can change this 1 to 0. And the bigger improvement, I think, is the dependency on gamma, the Euler genus, used to be linear, but now it's sublinear. It's not, it's more than sublinear, it's square root of gamma. It's the square root of the Euler genus. But if you actually look at this proof, what we actually proved is if you give me some graph on some surface with Euler genus gamma, and if the girth is at least L, then we can do 0, comma, something big O of square root of gamma over L. So this is natural, right? If your Euler genus gets bigger and bigger, of course you will need, the second part will need bigger and bigger maximum degree. And if you have bigger and bigger girth, that means your graph is sparser and sparser. So it should be easier to color it. So this R over L is somewhat natural, and we were able to prove that this square root.
This is for L at least 7, right?
Yes, L at least. So I'll just skip this lemma. So what's left? What's left to do is, for planar graphs, I have this giant big table. So solving any entry on this table is good. There are, 17, 18 entries to solve. But maybe the most interesting one is this. Finding the threshold where planar graphs become colorable, become a 0, 1 colorable. It's either 10 or 11, and we don't know yet. But there's one more thing. I was looking at this table, and maybe, I don't know, this is a good question. I'm not sure if it's true or not. Is there another jump? So if you look at the first column, there's a jump from 7 to 8, and now suddenly from 8 there's no 9, and it jumps to either 10 or 11. But in the other column, it starts from 5, and maybe at some point we expect it jumps to 6. But here we know it's 5, then it becomes 5 or 6 or 6 or 7. So it will be really interesting if from this 5 jumps to 7. Right? Maybe the threshold on here, there's no 6. So figuring out if there's a second jump in this table would be very interesting to me. So we did something about planar graphs, so we should do something about graphs on surfaces. And then I was saying this theorem. So this is what we actually proved when girth is very large. But then we weren't able to find any examples where this is tight for any L at least 8. So we suspect maybe this is not the correct growth rate, right? Maybe you can do better. Maybe the square root shouldn't be a square root, but maybe gamma to the 1/3 or maybe 1/4, something that grows quicker or slower, depending on how. So we conjecture that if you give me a graph on some surface with large girth, then you can partition in 2 parts, and the second part can be gamma of some function that depends on L, where that function grows faster than this. And we know that there exists some lower bound, because there's this result by Gimbel and Thomason, where they say if your graph, they prove the existence of graphs on surfaces that have large girth, that are not this number colorable in the traditional sense, in the classical proper coloring sense. But we know if you're not this colorable, then you're not 0k colorable as well. Because if you're 0k colorable, you're k plus 2 colorable. Because if you're 0k colorable, you just use one color for the first part, and because the second part has maximum degree k, you can just use k plus 1 colors. So k plus 2 colors in total. So we know there's a lower bound on this function of L, but we're not sure how tight this is. Maybe there's certainly a huge gap between 1/2 and something like this, or L to the 1/2. And then there's one last question, where so everything here was very general. We talk about graphs on general surfaces, surfaces of Euler gamma, Euler genus gamma. And maybe now we can do something exact, right? Maybe you leave the plane and you go one up, maybe the projective plane or maybe the torus. So in this paper, which I cited a couple times already, they proved that every graph on a torus, you can partition it into 5 parts, where each part is a induced matching. And they also generalize their own results. Remember, they prove, they prove Cohen and somebody else's results, where they prove that planar graphs are 2, 2, 2 colorable. These people prove that not only planar graphs, but graphs on a torus are also 2, 2, 2 colorable. And then they ask this explicit question. So our graphs on a torus, can you do something in between this and this? Can you shrink the tuple size from 5 to 4? And can you shrink the 2s to 1s, sacrificing one more color class? And this is all I have, and these are the people involved.
Thank you. Questions for Ilkyoo?
So you went to girth and avoided maximum average degree.
Yes.
But we know maximum average degree is really convenient for discharging arguments. Was girth easier to work with
Yes.
than maximum? Okay.
Because, I mean, if you do it with maximum average degree, it applies the girth. So the maximum
Yeah.
average degree is somehow slightly stronger. So we were working on the girth version because it was more convenient and we didn't want to be too ambitious.
Okay.
Somehow, because if you use maximum average degree, then you can't use the faces.
Right, yes.
But
Yes,
if you are a
have
graph
no
on a
control over
surface,
this.
you have these faces. Right? So we wanted to utilize these faces.
Okay. Probably a lot more convenient using the faces than it is trying to find irreducible configurations.
So when you're finding reducible configurations, if you do the maximum average degree version, there's no embedding involved. But if you do the reducible configurations for the embedding version, where you have these faces, then you can say something about the faces and it gives you a little bit more power. Yeah, so you can generalize everything to maximum average degree.
You had the conjecture for torus. Do they also have something for projective plane?
No.
Or they skip that?
They skip that.
They I only oriented.
Yeah.
Any other questions? No, let's thank Ilkyoo again.